So this one is, let me read the little paragraph at the beginning so we can know what we're being given here. The rate at which water leaks from a container is modeled by, now they do this a lot. They'll say the twice differentiable function. What they're doing is just saying everything's good. The function's differentiable, so it's also continuous. Like basically when they say this, they're just saying there's no issues or problems. Function R, where R of t is measured in gallons per hour and time is measured in hours from 0 to 1. And you can see that here's 0 to 1. Here's the important thing to understand here. They said that it is a rate. And notice that the units are gallons per hour. A rate is going to be something per something else. So they gave us a rate. So let me just write off to the side here. R of t is in gallons per hour. So if we do a derivative and get R prime, what are going to be the units? If it's already gallons per hour and we do another rate of change, what are going to be the units? It's kind of like this is velocity already, like it's a rate. So if we did a derivative of that, we'd have like an acceleration. So what are going to be the units if we do a derivative? Yeah, good, perfect. So it would be gallons per hour, like you did another rate of change. It's like they gave us velocity. They gave us the gallons per hour. If you want to think of that like feet per second, you know, just gallons per hour instead. So if you do a derivative, you're going to get gallons per hour. If you go backwards and you do an integral, what are those units going to be? Yeah, good, perfect, just gallons. So we would have gallons and then gallons per hour and then gallons per hour squared. What they gave us was this one in the middle. It's kind of like position, velocity, acceleration. Actually, not kind of, it's exactly what it is. Position, velocity, acceleration. So if we do a derivative, we're going to get gallons per hour squared. If we do an integral, we're going to go backwards and just get gallons. That's what's going on here. They gave us a rate. So values of R of t are given in the table above for select values of time. So letter A, use the data in the table to find an approximation for R prime. So first of all, R prime, that means gallons per hour squared. So show the computations that lead to your answer include units of measure. So these are going to be our units of measure when we get an answer. I can't actually take a derivative because I don't have a function. All I have is this random collection of points. So how can I approximate a derivative? If I can't actually take a derivative, what does a derivative mean? Derivative means what? What does it boil down to? What can we find since I can't actually take a derivative? Think back, what does a derivative mean? A derivative is what? You've been doing this for years and years. It is back from Algebra 1. Real basic, good, slope. Derivative means slope, awesome. Okay, so we are gonna do a slope around 1/2. Now 1/2 isn't in this table, so 1/2, you need to figure out where 1/2 would be. A half would be in between a third and 2/3. So a half would be, you know, somewhere in between that. So we're gonna use these 2 points to do the slope. And so I'm going to write them out. We've got 1/3, comma 8, and then we've got 2/3, comma 5. Those are the 2 points that we're going to use, and we're going to slope them. So it would be 5 minus 8 over 2/3 minus 1/3. When it says show the computations, those are the computations. You don't have to reduce it, so don't. Like literally just leave that alone. And it said do units, which are going to be gallons per hour squared. All right, so we approximated the derivative. Derivative means slope. This was gallons per hour, so the units would be gallons per hour squared. All right, letter B, use a left Riemann sum with 3 subintervals indicated by the table to approximate integral. Okay, so now we're doing an integral, so the units of measure are gonna just be gallons. So when we do an integral, We're approximating an integral because it's a Riemann sum. Our units are going to be gallons. Now, these are your 3 subintervals. You can do them all separately if you want, but we can actually write it in the factored form because the subintervals are uniform. It's counting by a third. It's 0, a third, 2/3, 1. So I'm going to put 1/3 out front. And which type of sum did this say? A left Riemann sum. So for this first subinterval, the number on the left is 11. And then for the second subinterval, the number on the left is 8. And then for the third subinterval, the number on the left is 5. Again, you do not have to simplify that, so don't. It isn't worth it. If you mess it up, it's going to be wrong. It's not worth your time. You just put gallons at the end, and that's your answer. Now, they didn't ask this, but I'm going to throw this question out there. Would this be an under approximation or an over approximation? Look at what the values in the table are doing. We did a left sum, so is it under or is it over? And I'm going to wait until I get a few answers. I need for you guys to be here with me. Look at what these values are doing. 11, 8, 5, 0. And we did a left sum. Now you guys are all saying under. It's going to be over. Look, if these values are decreasing, we have 11, 8, 5, 0. This is something that's decreasing. And the left side is further up, so that would be an over approximation. We would say over approximation because R of t is decreasing, and this is a left sum. These values are going down. Are you guys with me there? And someone wrote to me privately, if it was a right sum, it would be under. Yes, the values are decreasing. So if we did a right sum that's lower down, then that would be an underestimate. So yes, you're correct. All right, but this one would be over. All right, letter C. Use the data in the table. Use the data. Oh, that's a typo as well. Let me go back and fix that. Use the data in the table to evaluate. All right, now this is an integral of a derivative. So those are going to cancel out. This is like one of the homework ones we did. We have an integral of r prime. That's just going to be r of t such that 0 to 1/3. And so it is upper boundary minus lower boundary. And we just have to go and find those values in the table. So r of 1/3 is 8, and then r of 0 is 11. So it's going to be 8 minus 11. They didn't ask for units, so you don't have to put them, and you don't even have to reduce that. So you can just go ahead and stop there. All right, and then last one, they've got one of these crazy sums here. This is a right Riemann sum with n subintervals of equal length. What they're asking is for us to write this as a definite integral. And I'm going to make this dt instead of dx because this was r of t. If you wanted to make it r of x and put dx at the end, that's fine. I'm just going to go with dt since that's what the problem said. So remember, this is where it starts. This is our a value, this 1/4. So 1/4 goes there. And then do you see how this 1/2 matches here? The length of the interval should be 1/2. So if we start at 1/4 and our delta x is 1/2, what is our upper boundary going to be? If it starts at 1/4 and we want the length of it to be 1/2, what is going to be the upper boundary? Good, perfect. Nice job, guys. 3/4. And your function, all this stuff inside is going to be x. So or I guess t in this case. So it's r of t. The inside part is just r of t dt. And that's it. Those are problems that look super complicated, but are not actually that hard. This is the a value, 1/4. We wanted the delta x to be 1/2. So 1/4 plus 1/2 is 3/4. And then the inside part was just r of t. All this mess inside is the variable, so r of t dt.